Couple of quick announcements. So in case you didn't catch it in lecture this morning, both Professor Sanford and I worked out in the seminar this evening. So that's in the chapel instead of in Graves at 7 o'clock. The Hope College alumnus and Chem Department alumnus David Paul is giving the presentation this evening. So if you head to that and you write up an extra credit report, just kind of summarize what you see, what you think, submit that on Moodle, and that's worth an extra credit report for you. So especially those of you who have difficulty making those Friday afternoon events, this is the perfect time. And to trek across through the Arctic tundra to get to chapel to listen to that presentation. So take advantage of that. The other thing I'd like to give you a heads up on is that you will have your first quiz this week in lab. So don't forget about that. For the most part, that's going to be at least somewhat over experiment 18 and also incorporate the first part of VIDIG that we're going to talk about today. Okay, so your prof may give you some more specifics on what that's going to cover, but ultimately those are the ones that are pretty much going to be, at least they might be more specific, but be prepared at the first half of the VIDIG experiment and then experiment 18 that you did last week. All right, any questions on that? All right, so today what we're going to be talking about is experiment 17. So this is the VIDIG reaction. Okay, and so first things, I'll hit this a few times and I will say it repeatedly. Georg VIDIG is German, and so that W, just pronounce it like a V. Unless you're in Stanford section and she'll pronounce it as a W, and maybe she can explain why. But ultimately, so we'll be doing the VIDIG reaction of ester-stabilized ylids. Okay, so there's a lot of things in there we don't know yet, and we'll cover those here as we go. All right, so just a quick little game plan of what's going on. This week is experiment 17, part 1. Okay, so that's essentially we're doing 2 parts to this experiment. I'll kind of give you some more details here on where we stop, but ultimately we'll do half of experiment 17 this week. We'll do the other half next week. Okay, and including, like I said, quiz 1. Also, we'll be doing NMR processing for those of you who are chomping at the bit trying to identify what your unknown is. You do not get your NMR data from your professor. Instead, you're going to learn how to take that data and actually process it yourself to turn it into an NMR spectrum that you can interpret. Okay, so we'll be doing that during lab this coming week. Okay? And you will also have some other, all your 18, what else is left? GCMS, you'll be getting that back from your professor this week. Okay? All right, and what we're going to do today, we're going to do run through experiment 17, then we're going to look at look back at experiment 16, what you need to do there. Keep in mind you'll be doing the pre-lab for all of experiment 17 this week. Okay, so there's some new equipment in there that we won't be using this week, we'll be using next week. Be sure you put that in there as well. All right, and then looking ahead a little bit, so next week we'll be doing experiment 17 part 2. Okay? But really what's important is experiments 18 and 16 are both due next week, either Tuesday or Thursday in your lab section. Okay, so please take note of that. You will have everything you need to do experiment 18, once you finish lab this week, so including that NMR. And then experiment 16, I'll run through some examples there, and you can do that anytime. Okay, so there won't be anything in your labs about 16 beyond what I talked about today. Okay? All right, and then next time we'll talk a little bit about NMR interpretation of experiment 17. So we'll do that next week as well. All right, any questions on the game plan? Perfect. All right. So with that, this is the VIDIG reaction. Okay, a couple of components that I'm going to highlight here for you. Okay, and yeah, this is a little bit of a challenge of PowerPoint. You should probably write this down at least in some sketch format. Okay, so over here on the left, this is called an ylid. Okay, so that funky looking name, you pronounce that ylid. And what an ylid is a species that has adjacent negative and positive charges. Okay? But it's at least a relatively stable species. If you look at that, what makes it an ylid, okay, is it looks like you should just make a bond between them, right? Which you can draw it that way, but ultimately this way, those are both full octets on those adjacent species. Okay, so note that if you do the double bond, now suddenly you have extra electrons around the phosphates. Okay, so typically an ylid is drawn like this with separated charges. The other reason that we do that is that really gives you a hint on how that thing reacts, and we'll see that here in a few minutes. Okay? So the ylid is one component of the VIDIG reaction. The second is either a ketone or an aldehyde. Okay, so I've got R and R prime written here just in the generic sense. Okay, that's going to be either a ketone or an aldehyde. Okay, these two things will react together, ultimately giving you a double bond, an alkene, okay, and then this leftover triphenylphosphine oxide. And so, to kind of give you the quick synopsis of what happens, is the carbon of your ylide that has the negative charge is bonded to the carbonyl carbon, and ultimately you make a double bond between those two. I'll show you the mechanism here in a couple of seconds, and that'll kind of explain some things. All right, a little bit of explanation of species in here. So like I said, an ylide is a neutral species with full octets and yet adjacent charges. Okay. This is one that you're going to see. This is by far the most common. Every once in a while you'll see a sulfur ylide or a couple other things that we might touch on later in the semester. Okay, but this phosphorus ylide is by far the most common and the one you'll see with the Wittig reaction in a couple of weeks in lecture as well. Okay. All right, some other things is we refer to stabilized and unstabilized ylides. Okay, and this has to do with the stability, okay, of these species ultimately. Okay, so an unstabilized ylide typically has these two groups on it that I've labeled Z and Y, are just like alkyl chains. Okay, so you put two methyl groups on there, for example. That's what's referred to as an unstabilized ylide. Right? And the reason that's unstabilized is because it behaves a lot like a C minus, right? So we know from what we talked about alkyl groups or say alkyl lithium reagents, for example, in the first semester, that those are very, very sensitive. Okay, they're air sensitive. They'll grab a proton for pretty much anything. They don't last very long. Okay? So the same thing happens here is if you have two alkyl groups there, okay, it's going to end up being air and moisture sensitive. It's difficult to handle. Okay? Lucky for you, we're not using those in lab this week. Okay? What we're doing instead is what's called a stabilized ylide. And the key is when that's when the anion here is stabilized by resonance. So there's either the Z or the Y group, whichever one you want to use, has some sort of a carbonyl species there. You can draw resonance structures that stabilizes everything. It becomes less basic, less nucleophilic, okay, less reactive. Okay? It still works really, really well in the Wittig reaction, okay, but it's not as prone to those nasty byproducts that you can get if it comes in contact with water or air or something like that. Okay? So we'll get some more details on this one as we go forward. Okay. All right. Any questions? Lovely background. Okay. All right. Okay, and one thing to note, and this is actually the driving force of this reaction, is the byproduct that's formed here is triphenylphosphine oxide. Okay, and so I've drawn it out here in kind of its chemical structure roughly. It's also, you'll see it as this PH3P PO species. This is ultimately the driving force. That phosphorus oxygen double bond, or you can also draw that as an ylide as well. But that phosphorus oxygen double bond is a really, really stable bond. So this triphenylphosphine oxide is a rock. Okay, you form that, and it's a white solid, and this drives the reaction forward. Okay? You will become familiar with that white solid, and it may become the bane of your existence this week. Hopefully not, but it can be a headache. All right. Okay, so there's a couple of different steps. How do we make that ylide? All right, so just as a reminder, the ylide is over here. Okay? We typically get to it by first putting the triphenylphosphine group on and then doing a deprotonation. We'll go through this a little bit more in lecture in a couple of weeks, but long story short, if you have some sort of an alkyl halide, you treat it with triphenylphosphine, and it does an SN2 reaction. Okay, so the phosphorus just comes on over, attacks that carbon, kicks out the bromine, and gives you this, what's called a phosphonium salt. Okay. So this week we will not actually do that first step in lab, and instead what we will do is we will start with this phosphonium salt here. Okay, so we'll start with that. Okay, so we're going to take that salt, and then what you do is you treat that with a base. Okay, because you have this phosphonium salt here, these two hydrogens next to it are more acidic, far more acidic than a normal proton like CH bond, a normal carbon-hydrogen bond. Okay? And so a mildly strong base, so a alkoxide base, so in this week we'll use sodium methoxide, that will pull one of these two protons off and then give us the ylide. And so that's just removal. Keep in mind that there's two hydrogens here, And then in the final ylid, there is one hydrogen in addition to this argon. And again, I'll give you the specifics of what we're working on in the lab in a couple slides. All right. And so as mentioned, this is an SN2 reaction right here with all the benefits and detriments that are attached to that. Okay, so you essentially need to use a primary, and you can sneak into a secondary halide to do this. Tertiaries definitely don't work because, like I said, it's a straight SN2 reaction. All right, and again, stabilized is just to give you an example of the ones that you can sort of use as a counterpoint here. This is a stabilized ylid. This is the example of the one we're actually going to use in lab. And now, of course, you can draw the resonance structure, kick those electrons in and up, and that's what makes it a stabilized ylid, because you can draw both resonance structures. So that would be definitely one that I would be familiar with. It's a classic favorite for profs on the lab exam, quiz, excuse me. Give an example of a stabilized ylid, or draw the stabilized, a resonance structure of the one that we're using this week, or something like that. Okay. So it's good to be familiar with that resonance structure and what makes it stabilized. Okay. So if you can draw that resonance structure, it's stabilized. If you can't draw the resonance structure, then it's considered unstabilized. Okay. All right. And so, like I said in lab this week, what we'll do is we'll start with the ylid of this species. The phosphonium salt of this species, and then treat that with sodium methoxide to make the ylid. All right, and then if we get to a little bit more background, okay, yeah, as I mentioned, there's extra stability and nice light. All right, a little bit more background as to how this reaction works. So at this point, it's still a little bit messy. As some background, as I mentioned, here's Georg Wittig, so the actual pioneer of this reaction, in addition to several others. Okay, and so. He died a couple of decades ago, was awarded a Nobel Prize primarily for this reaction. Okay, so at the time that this reaction was first developed, there was no other way to kind of take, to do anything to put large molecules together in this fashion. And not only can you do large molecules in this fashion, it's something that's straightforward enough that we can do in the organic lab, right? There's no dangerous reagents in there. There are some, there is an excess of byproducts that are formed, okay, but they're innocuous byproducts and they aren't going to hurt anybody. Okay, so it's a really straightforward reaction that you can do pretty easily. Okay? How does this happen? All right. The first step is we have the interaction of the ketone or the aldehyde there with the ylid. Okay, so those come together to form this species that's called the beta-ene. All right, give me just a second. I'll actually draw how that works. All right. And so what happens is this is simply a nucleophilic attack of that ylid, of the negative charge on the ylid, over onto the aldehyde. And so if you're pushing arrows, you bring that over, that attacks there, and that kicks up. Okay. And so that gives you this very specific species called a beta-ene. And this is one of those things that organic chemists do sometimes, is there's arguments upon arguments of whether that species actually exists or not. Okay? And the reason is there's a really, really quick reaction that happens next. You have a positive charge and a negative charge, they can snap together. Okay? And so ultimately, after lots of arguing and different things, this species can be intercepted in some ways to give other products. And so there is at least a pretty reasonable evidence that this is formed as a discrete intermediate. Okay? But it doesn't live long. What happens is that oxygen simply attacks the phosphorus over like this. Okay? And it makes this four-membered ring. And so now that four-membered ring, you can see that we've connected the two carbons that are ultimately going to be connected. We've connected the oxygen and the phosphorus that are ultimately going to be connected. And now this is pretty much just sort of like a swinging gate mechanism. Okay, so if you look at this four-membered ring, ultimately the bonds on either sides of this just collapse and give their electrons to the two newly forming pi bonds. Okay, so the newly forming double bonds. And so what happens is, say the two electrons that are between the carbon and the oxygen here, those flip up to make a new oxygen phosphorus double bond at the same time as these two between the carbon and the phosphorus drop down and make the carbon-carbon double bond. And so just to draw that out, those two go up there and those two go down there. Okay, so those two bonds just sort of like flip. And so if you draw it out without rearranging it like I did to go up to the product here, okay, so ultimately that then gives you the product. If you just kind of draw it, and sometimes it can help to draw them in the same orientation as your previous structure. What that then gives you is, there's the triphenyl phosphine oxide, and then the alkene. Okay, so you can see that basically those electrons just flip, okay, and it opens up that ring and gives you these two species. Okay. And so as you can imagine, what do you think is going to react faster in this reaction? An aldehyde like this or a ketone? Okay, an aldehyde. Why an aldehyde? It's an issue of sterics, right? So you can imagine that these are going to be kind of sensitive to what these groups are down here. Typically, this method will allow you to make di-substituted alkenes really, really easily. And that's what we'll be doing this week. You can make tri-substituted. When you get beyond that, it starts getting kind of troublesome. Okay? To fit 4 groups around there is very, very difficult. All right. Anybody have any questions on the mechanism? How you get this to work? This is another one. You should be familiar with the steps of this mechanism and how you make these two products. All right. All right. And I will remind you, if I'm a little too quick going through these, all these slides are up on the Moodle site as well, so you can go back and review them. And heck with that, we also have the video, so you can go back and review this to your heart's content. All right. So what you're actually doing this week? Okay, so these are the actual structures that you'll be using, and so I showed this one before. This is your phosphonium salt. Okay, so what comes out of the bottle is a nice white powder. Okay, it's actually a phosphonium bromide. I left off the bromine anion here. Let's chuck that in. Okay, and like everything else in organic lab, this is a nice white solid. Okay, so that's one of the reasons that we use this illid and choose this is this. That's a very nice, easy to handle, very stable reagent. Okay, there you can see the whole name of this. Okay, so when you're looking things up in terms of your what's the molecular weight and doing that sort of thing for your table of reagents, be sure you chalk that down. Okay, it's also in your lab manual, so don't worry if you don't chalk that down too quickly. All right, what we will do then is put this into methanol and then add sodium methoxide to it. Okay, what that does is it does the deprotonation. Again, you've got 2 protons down here. Pulls one of those protons off. Okay, gives you what's called the enolate, this illid here. Okay, couple of notes, hints and tips on this. Okay. Because these are not super sensitive, but they are relatively reactive species. Some of the things that we do to sort of help those out is we use dry methanol. Okay, so note that we'll have a specific bottle in the reagent hood. Okay, that was anhydrous methanol. At least it was anhydrous until we popped the top off it earlier today to set it out in the lab. Okay, but there's relatively small amount of water in there. Okay, that'll help. More water in there causes different byproducts. Okay. So you'll want to use dry methanol there, not the stuff from the red cans in the shelves. The second thing is the sodium methoxide is a solution in methanol. Okay, it's a 0.5 molar solution in methanol. Okay, and you have things really easy this week is there's a little kind of like a hand pump thing that's used to dispense exactly the amount that you need, and you can put it directly into your round bottom flask. You'll ask why we don't do this for every single reactant all semester long. But it's just to minimize, this is a caustic material, it's basic. Right? Again, it's not enough to burn holes in your hand or anything super exciting, but you don't want to handle it with your bare hands either. Okay, so we use the pump to get that. You can dispense it directly into your flask. Your prof will show you how to use that during your lab this week. Okay. All right, so ultimately you stir these together for a few minutes. This is a very fast reaction. In the order of 5 minutes, it'll be all done. Okay. Then the next step is the Wittig reaction itself. Okay, so we take this and we react it with, this is called hydrocinnamaldehyde. This is the aldehyde that we use this week. Okay, it's going to be a relatively small amount of this. It's only about 3/4 of a milliliter. So either a TA or your prof will dispense that with a syringe for you. And we just try to keep the number of needles flying around in organic lab to a minimum. So the profs will do that for you, or the TAs. Okay, and when those react together, now this is the mechanism that you should at least be familiar with. Okay, this illid carbon, the one with the negative charge, is the one that's going to attack that aldehyde carbonyl carbon. Those are the two carbons that will come together with the double bond. And one of the little hints I will give you is be sure you count those carbons on both sides and make sure that you don't have things disappearing or adding or something else. Okay? So just to keep track, this one here is the one that's on this side of the alkene ultimately in the product. Okay, on this side I have two CH2s and then the carbonyl carbon, and that matches my product over here, CH2, CH2, and there's what was the carbonyl carbon. Okay. All right, and of course we got the ubiquitous byproduct, the triphenylphosphine oxide that's over here on the far right. All right, I've got that squiggle shown on my product. What does that mean? Okay, that there's isomers there. What sort of isomers can I make in this product? Yeah, I can make cis and trans. When you end up with like unsymmetricals, because if you have a ketone, you know, that has methyl groups on both sides, of course there aren't isomers. Okay, in this case, we make two different isomers. Okay, so you can make the trans or the cis isomer. So we got them both shown up here. So based on your fount of chemical knowledge that you now have, which one is going to be the most prevalent species? Probably the trans, right? Because that's the one that's the most stable. Okay? Turns out that because of the mechanism here, that first step really dictates which one you get. Okay? And so it's not quite as pronounced as it might be in some other reactions that are very, very reversible and things like that. Okay? So you will see both of them will be present, and you're going to have the fun and excitement of figuring out how much of each one based on your NMR next week. Okay? So we'll get to that later. But ultimately, you will have a mixture of these two isomers. All right. Okay, and as I mentioned, the ratio depends on the reaction conditions. What you will find is, for the most part, you will get similar ratios, but every once in a while somebody does something a little bit different, and you can see relatively dramatic differences from person to person. So, all right, but you will see both of them almost guaranteed. Okay, some hints and tips as we do this. Okay, for this step of the reaction, this is a little bit slower. That first step, the deprotonation to make the illite, is very, very fast. Okay, this reaction is a little bit slower, and so what we do is we reflux this reaction, okay, using a hot water bath. Okay, so take note, it'll be a hot water bath and not the heating mantle here. Okay. Once you get this reaction done, you'll see all these heaps of white solid around. This is just like that experiment in the first semester where you made we used the NBS and you had all that beautiful white byproduct that was just a waste. Okay, it's the same thing here. Okay, all the white solid that you form is all the triphenylphosphine oxide. And as much, it's a pain to get rid of, but as I mentioned before, it's what drives this reaction forward. So what we'll do is we'll remove that by gravity filtration. One thing I really want to note is be sure you cool it completely before you filter. Okay? If it's still warm when you filter it, what's going to happen is some of that triphenylphosphine oxide will still be dissolved in your methanol, and it will go through the filter because it's still dissolved, and then it will crash out after the fact. Okay? So then you'll end up filtering again. If you drag a little bit of your triphenylphosphine oxide forward, that's okay. Okay? But you don't want huge heaps of it because then it can mess things up next week. All right? The second note is don't filter in oil. So every once in a while we'll have these things that'll oil out and you'll get kind of multiple layers and things like this. So if it doesn't look like pretty much a homogeneous solution with solid white stuff floating around, if you see like something that looks like 2 layers or something like that, be sure you talk to your lab prof and figure out what to do with that before you try and filter it. Okay, what can happen is if there's oil in there and you try and filter it, it can stick to the filter paper, and that's pretty much all of your product that's stuck there, and you're going to have a difficult time getting it out of there again. Okay, so if you see what looks to be 2 layers of liquid before you do this filtration, talk to your lab prof. Okay, they'll help you out with that. All right, a couple of other things. You may need to filter multiple times. And again, it's worth a little bit of extra effort this week because then next week when we separate and clean this up based on column chromatography, if you have too much triphenylphosphine oxide left, it can clog up the column and make your life miserable. Okay? Little extra work this week is definitely worth it so you don't have a major headache next week. Okay? And again, don't throw away your filtrate. So when you do this, like I said, you'll be doing this by gravity filtration. You'll run it through, you'll have all this beautiful white solid in your filter paper. That's organic waste. Okay? The stuff, the filtrate that goes through, that's where your product is. So keep in mind, it's always a great habit to get into. Follow where your product are, where's the important thing in the reaction, where can you find it at any given step. All right, I think that is about it. And so what we'll do is at the end of this week, we will end up with this product first of all, in the filtrate, and then we'll take the next step here, is we're going to use the Rotovap. This is the answer to all of your dreams and requests. Okay? Those of you who hate all those distillations, we will have you do one more distillation this week in terms of getting off some of the methanol. Okay? But this is ultimately like, this is what you've been waiting for. Okay? Do you have to do the distillation to remove hexane? No. Okay? And I'll show you that in a second. And then finally, we'll want a TLC of your crude product. So at the end of the day, you will distill off your solvent using a Rotovap. You'll have a little bit of oil that's your product. We'll do TLC on that to kind of gauge what the purity is, and then next week we will purify that product. Okay, so more information on that next week in lab. Okay, all right. Back to that Rotovap. What is that? This is what a Rotovap, kind of looks like. We have several different models in the lab, and they're all slightly different, but they have several things in common. Okay? So there's a vacuum pump. So there's not a vacuum pump connected to either of these, but ultimately there's a vacuum pump that reduces the atmospheric pressure, or I guess the pressure, inside the apparatus. So what you'll do is you put your material down here on the bottom of the Rotovap, or you can see you attach your flask to this. Okay, this part right here is what's called a bump trap. Okay, so if something would happen in your reaction, and once in a while if you boil something, all of a sudden it'll kind of spatter. Okay, if it does that, it goes up into this trap and then goes back down rather than spattering throughout the entire instrument. Okay? And also okay, so we've got the vacuum pump. It'll reduce the pressure in here. We cool this part up here as a condenser. And so then your solvent that is distilled off basically hits the cooled condenser and drops down into this collection bowl. Okay? And the most beautiful part is instead of setting up your entire distillation apparatus and going for 20 minutes, a half an hour, whatever, typically for something like methanol or hexanes, it pulls things off in probably 5 minutes. Okay? And you can just sit there and watch it the whole time. It's mesmerizing. You'll see. All right. So what happens is we got the vacuum pump. That'll reduce the pressure inside. Rotation. So that's the roto part of the Rotovap. Is this part down here? There's a mechanism in there that'll turn that. Okay, and as a result, in theory, what that does is it kind of ensures consistent boiling. It's sort of like stirring your distillation pot. Sometimes it works better than others. Okay, so if you keep that stirring really pretty quickly, keep it nice and agitated, you'll get a nice, smooth evaporation of your solvent. Okay. Typically, we use a hot water bath down here. It can serve as a heat source. Again, depending on the solvent that you use, you don't even necessarily need that. Okay, or you can just keep it at room temperature. You can imagine as you do this, as you're evaporating solvent, the vacuum pulls it off and it condenses over here. Your flask will cool, right? So you're pulling energy out of it by doing that evaporation. And so it'll get cold if you don't put it into the water bath. So at least be sure that you always, whenever you do a Rotovap, you always have that flask in the water, okay, in the water bath. Okay? We'll show you in lab exactly how the mechanisms work of, raising this part and lowering it into the bath and things like that. Okay? And then finally, the condenser. Okay, this part back here is chilled either with circulating ethylene glycol. So the 2 in 3129 have ethylene glycol in there. The 2 in 3109 on the other lab have some dry acetone mix in there. And so what they do is they basically cool the solvent up here, allowing it to condense back into this bulb. Okay. Like I said, long story short is that this enables you to distill things in a big hurry compared to the standard atmospheric pressure distillations that we've been doing for the last several months. Okay? So the Rotovap will be your friend. All right, any questions about that? Okay, basically at the end of the day, you're going to end up with an oil. You'll do that TLC to get a baseline idea of how pure it is, and then we'll take that material next week, so be sure you save it in a vial or something like that. Next week, we will be doing the column chromatography to purify it. All right, so with that, just as a quick little recap, we already talked about that. Be sure you do the pre-lab for all of 17. So be sure you give it a read through all the way, okay? And get that pre-lab for the whole thing. All right, for experiment 18, okay, just as a quick little recap, you'll be getting your GCMS this week from your instructor. If you don't already have them, some of you might. Okay, you'll process the NMR in lab this week, and so that'll get you the start on figuring that out. And then again, I'm going to emphasize this one more time. Be sure you use that data to then determine what the identity is. Then use literature spectrum to confirm it. Okay, so be sure that you interpret your IR and say, because of this peak, it says that I have this functional group. And because of this, it says I have this functional group. Do the same sort of thing with the NMR. And then as a wrap-up, confirm it by comparing it to literature spectrum. Okay? In the past, we've had some folks who say, well, I had 3 propanol, that isn't even a compound, 1 propanol because it matches the NMR. Okay, what we want you to do is interpret that NMR and then match it to confirm. If that makes sense. So interpret all of your data and then say, hey, look, I'm correct. Okay? Any questions with that? All right. So what we're going to do is we're going to switch gears here really quick and talk about experiment 16. All right, so experiment 16. How many people have at least looked at experiment 16? There's a couple ambitious ones among you. All right. Okay, for the rest of you who haven't, okay, so this is basically an overview of NMR, of how to, what to look for, how do we calculate NMR shifts, and so on. Okay. One thing I will tell you, and I'll kind of emphasize as we go through, these are empirical ways of predicting NMR spectra. Sometimes they work really well, other times, they're okay. Okay, so kind of keep that in mind as you go forward. They're another tool to help you. Okay? All right. Okay, so we covered the basics of NMR in lecture. Okay, some of the new aspects that we're going to talk about in lab here is the empirical prediction of chemical shifts. So especially those of you who are in my section, basically I tell you a broad identification of where chemical shifts are. You should be able to tell if something is closer to 2 or to 7, right? But you don't need to tell me that it's actually 2.36, right? So just that general idea. This will help you predict a little bit closer, okay? Sometimes. All right, and then we'll talk a little bit more about coupling and more complex splitting patterns and actually using kind of data and specific numbers to figure that out. All right, and one little quick note. To find your actual chemical shifts, if you go through the worksheets, it will ask you to predict it and then to say what the actual shifts are. First, you're not going to go into the lab and run the spectra. What you're going to do instead is use either SDBS or Aldrich Spectral Viewer to figure that out. SDBS you can access simply by Googling SDBS and it'll pop right up. The Aldrich Spectral Viewer I think is available on any of the campus clones, so it should be available under the chemistry programs on any campus computer lab. Okay, so you can check that out. Either one of those are reasonable sources that when you put in that actual chemical shifts, you can look up the data on these sites. All right. Okay, so this is what it kind of looks like. All right, so what we're going to do is I'm just going to walk you through an example of how do you calculate, how do you predict an NMR chemical shift. There are tables on page 16-9 through 1611 that you definitely need to do this. Okay? And so we're going to give you, I'm going to run through a quick example right here, okay, on how we use those tables to predict chemical shifts. Okay? And so what we're going to do is we're going to do one example with an aromatic species, okay, and that's the table that's on page 16-10. And then we're going to do one example of an alkyl group, and that's using the table on 16-9. The one on 1611 are double bonds, so if you have alkenes. All right. So this is what one of those tables looks like. Okay, so this is the one that's on 16-9. Okay. How you figure out the chemical shift? This is just plug and chug. Okay, so the chemical shift for these two, for a CH2 group, as shown right here, you calculate it with this little equation. So you start out with a base value of whatever's there. So in this case, it's 0.23. You'll see that it's different for your aromatic species and your alkenes. So you start out with that value right there, and then you determine the coefficient for those other two substituents that are on it. You determine what those numbers are, and then you add them all up. Okay, it's pretty straightforward. Okay, so in this case, we are looking at that proton, those two protons right there. We want to predict the chemical shift of those two. Okay? What we'll do is on one side, we have an oxygen, okay, that's attached to an aromatic ring. On the other side, we have a methyl group. Okay, the CH3. Those essentially are your X and your Y species. Okay, so the two that are on either side. All right, there's the equation. Now what we do is we look through that table and see the thing that matches the closest to what the substitution is. Okay, turns out that they have a substituent that is just a CH3, and that has a value of 0.68. So go ahead and you plug 0.68 right in there. The other side is this oxygen that's attached to this aromatic ring. That's the OAR. So AR is shorthand for an aromatic ring. And then you plug that number right there into that equation. You simply add them up, and that's your predicted chemical shift. Okay, the two substituents there, I tallied the numbers over here. You add those two together, you add the 0.23 on there, boom, boom, boom. You expect that chemical shift of that compound to be at 3.85 parts per million. Okay, so it's really pretty straightforward. One thing I would caution you is that these are pretty specific. Okay, so the calculated, amount, the shift for a methyl group is different from a regular alkyl group. So, and I think that's 0.058, I believe. So it's a little bit different. You go in here. These are several different carbonyl compounds. Okay, if it's an alkyl ketone or an aldehyde versus an aromatic ketone. So they're really pretty specific. What these are based on is just like tons and tons of experimental spectra, and they kind of, it's an empirical method. So you put these together, you model them closely enough, and it'll give you at least a pretty good idea of what those shifts are. Okay? There's no like super, quantum mechanical methods or anything else like that used. It's just sort of back of the envelope. As a result, most of them are pretty good. Every once in a while, you get one that's off by quite a bit. Okay? So just gotta keep that in mind, that it's a quick and easy method, but not necessarily a surefire method. Pretty good, but not great. Okay? Any questions on how that works? Okay, if you happen to be looking for, say, like a CH3 group, what that is, one of the two substituents here is simply a hydrogen. Okay, so you use that top line instead. Okay. So you can go through and calculate anything that's on an alkyl chain. Okay, so CH2s and CH3s. CHs are slightly different that we aren't going to deal with in the lab because that's a whole other table and a whole other bunch of fun. So we'll leave that to a different time. Okay, so we're going to stick here with just the CH2s and the CH3s. Okay. Any questions on this process? All right, so we'll ask you to do this a couple of times throughout the worksheets there, and then you can compare that to the values that you actually see in the literature. Okay, and you'll see, like I said, that they're pretty good. All right, what about for these aryl groups? Okay, these are a little bit more complicated. Okay, so we're going to look at what the chemical shift of that one is, this HA. Okay, so now same general idea. We've got the equation up here on the top. This equation could be a little bit deceiving. Okay, keep in mind that there are 5 different substituents on an aromatic ring, not just 3. Okay, so you put this little thing in there and it kind of makes you think that there's only 3. But keep in mind that any hydrogen is going to have 2 adjacent ortho groups, 2 meta groups, and then 1 that's in the para position. Okay, so don't forget those. Okay, it turns out that it's kind of handy that if any of them are hydrogens, say like these 2 over here, that coefficient is 0, so you can kind of ignore them. Okay? But if you have a multiple substitution on that aromatic ring, you do have to calculate that value. Okay? All right, so now the same sort of idea that we're going to look at. If we're looking at HA, we have a nitrile that's attached to that. That's what the CN is there. And the nitrile's in the ortho position. So what we do is we look down the table, we find the nitrile down here, third from the bottom. Note that it gives you 3 separate values, right? That is whether it's ortho, meta, or para relative to the hydrogen that you're looking at. Okay, so in this case, we're looking at this HA here down on the bottom, so that nitrile is ortho to it, so we better take that first value that's in the ortho category. So those of you who can't really see these, that's ortho in the first one, meta in the second, and para over there in the third column. Okay? All right. With the hydrogens, okay, we can ignore those hydrogens as I mentioned. Okay. Then the other substituent over here, one is the nitrile, as I mentioned. We look at this one here in the ortho position. The other substituent up here in that meta position is that O-alkyl, so an alkoxy substituent. And we look at that, and that's over here. So we use this second value here because now I covered it up, but this column here in the middle is the meta values. So because that's meta to the hydrogen that we're trying to calculate, we use that value. Okay, so now we take those 2 values, we add them together. Yeah. One note is be careful with the signs. Okay, in the aromatic table like this and in the alkene table as well, some are positive and some are negative. Okay, so some drive that signal upfield, some drive that signal downfield. Okay, but ultimately we add those together and we determine that we predict that that HA should show up at 7.45 parts per million. All right. So any questions on how to do that? Hopefully that's pretty straightforward. Major take-home message, just be sure that there are 5. That's really the place where people get stuck. They'll do an ortho, a meta, and a para, and then they'll forget about the other 2 that are there. All right. Now we'll see how well we actually did. Okay, so if we look at this spectrum, this is the actual spectrum of these two, this compound. Okay, if we look at the predicted shift for the CH2 group right here, we said 3.85, and okay, that's in the ballpark, right? I would call that one closer to maybe about 4.1, but it's pretty close. It definitely helps us figure out where about we should find that peak. Okay, and another one, if we did HA down here, the predicted is 7.45. That's, again, it gives us right about there. So we're kind of close. Okay, so it can be, this is a good illustration. It can be a helpful guide, but not necessarily a bulletproof, assignment. What this is often good for is if you get a spectrum like this, it can help you assign all those peaks and figure out which ones are which. Okay? And we will ask you to do that on a couple of different things throughout the semester. All right? One other note. So when you start with the spectrum, and then you're reporting your data. So this week, when you get your NMR spectrum, okay, and you're going to report that data in the NMR data table, the way that most of the lab profs here would like you to do it is to start labeling your peaks from left to right. So when you have the NMR itself, label the peak that's farthest to the left as A, then B, then C, then D, and onward to the right. So from highest chemical shift down to lowest chemical shift. And so then when you go back and assign these letters on your structure of your unknown, then you can assign each one. Okay, this is HA, this is HB, and then everything matches up nicely, and it's easy to look at your NMR data table and tell which signal corresponds to which peak. Okay, so that's one little tip for you. And then, of course, remember that ultimately when you're reporting your own data, so when you get your own spectra like this and do some interpretation, okay, what you'll want to do is report that in an NMR data table. So this week, your professors will tell you exactly what they want in an NMR data table. It's going to look something similar to this, but then ultimately what you want to do is you want to put the letter in here, the chemical shift, then the literature chemical shift, and so on down the line. So they'll kind of be specific with that this week as they describe the process. Yeah?
With the literature chemical shift, do you want the one that we calculate with the formula or from like SPPS?
Yeah, from the database, the actual, like a literature sample. And that's the other thing is some professors, depending on the assignment, may also include another column that's the calculated value. Okay. So, and that's kind of, it depends on who the professor is and which experiment it is, whether they want that or not. Okay? All right, any questions with that? All right. Okay, so we're going to hit splitting here really quick and talk about a little bit more complex splitting. And so this worksheets here, the set, will also ask you to do some prediction of splitting patterns. Okay, so in lecture, for the most part, we talked about the three bond rule and the N+1 rule, that if you have adjacent carbons, you can figure out how many lines are in that pattern, okay, whether you get a triplet or quartet, things like that. Okay, we're going to talk a little bit more about some of the more complex splitting that you might encounter. All right, and what we're going to do, okay, so if we think about this CH2 right there. If you predict what the coupling of that proton is going to be, what do you anticipate? What's the signal going to look like? Okay, it's a quartet, right? So it has adjacent, this CH3 is next to it. You're going to get a quartet. That's pretty straightforward. Okay. Turns out that the aromatic species are a little bit more complicated. All right, but before we get to those, how about this CH3? What coupling do you expect from that thing? It's going to be a triplet, right? There's two adjacent hydrogens there. That'll be a triplet. All right, what about more complex? Okay. All right, so I'm going to go to something that has a little bit more funky splitting in it right off the bat when it has some of these alkene splitting. Okay, this is where alkenes tend to be where you start getting into a little bit of a mess. Okay. All right, so whereas in lecture I kind of waved over this and said, hey, if you have alkenes, it'll give you some interesting coupling patterns. Okay, we're going to give you some specific values here to look for in terms of splitting around alkenes. Okay, and this will help you assign your products of the Wittig experiment in a week here. Okay, if you have an alkene that has a cis orientation, the coupling constant between those two hydrogens is in that range of 8 to 12. Okay, so we can measure this using the NMR processing program that you'll see this week. Okay, if you see something that's in that 8 to 12 range, that suggests a cis double bond. Okay, in contrast, if we get that trans product, okay, we'll expect that coupling constant to be in the 12 to 18 range. And so I'll kind of give, as you're feverishly scratching these down, I will tell you that this table is in your lab manual. Okay, so you don't need to, you will see them, already written down as well. Okay. Some other splitting that you're going to see, okay, this is our normal 3-bond coupling. So if you look what's called, vicinal coupling. So if you have a hydrogen that's on an alkene here, it's 3-bond coupling to this one. There's free rotation around that single bond. Those typically, like free rotation splitting, tends to be about 7 or 7.5. It's kind of typical. So on the last slide with an alkyl chain, you typically see 7 or 7.5 hertz is your normal coupling. Okay, so if you kind of keep that in mind, this is normal 3-bond coupling. But when you have a rigid system, what you can also get is allylic coupling. Okay, so this is an exception to kind of the 3-bond rule, that you can get longer range coupling because of the way that things are held in a specific arrangement. Okay, so now in this case, if we've got, this is now 4 bonds. From this hydrogen up on the top, there's 1, 2, 3, 4 bonds to the allylic position down here. That gives you small coupling. Okay, this is one of the reasons that we tend to ignore it in lecture, because sometimes you see it, sometimes you don't. And the only way you can tell if you see it is to take the NMR and look. Okay? But that longer range 4-bond coupling with a double bond in there, that'll give you a small coupling between 0 and 3 hertz. When it comes time to do the interpretation of the Wittig spectrum, we do see some of this coupling on those. Okay? And that's kind of a special exception here because it's 4-bond coupling, longer than what we normally see, and that's because of this rigidity of that double bonding. Okay? All right. So now if we think, what are these things going to look like? So if we have HA, what is that splitting tree going to look like? So it's going to split with HB down here through what type of coupling? What's it going to be an approximate coupling constant of HA and HB? Okay, it's trans, so it's going to be in that 15 or the 12 to 18 range. We'll call that 15 hertz. Okay, it's also going to have allylic coupling. So HA will also couple with these 3 out here. So it'll give you a nice wide, 15 hertz coupling for the HA to HB, but then give you a nice little narrow allylic coupling for the quartet to CH3. Okay, and those are going to be really small, 0 to 3 hertz. Okay, if we look at HB for a second, what is that one going to look like in terms of the coupling constants? Okay, HB to HA, it had better look the same as HA to HB, right? So those are the same, it's reciprocal. Okay, so that's going to be trans coupling, and again in that 12 to 18 hertz. But then now, how far is the coupling between HB and this CH3 group? Okay, in this case, it's only 3 bonds, and so you will probably see like the normal vicinal type coupling down here. Okay, and so that's going to be more like 7 hertz. Okay, so we'll have the trans coupling and then the vicinal coupling. Okay, now what are these things going to look like? Okay. All right. So this is actually, if we go ahead and draw those splitting trees, if you actually want to draw this to predict it out, you can do it, draw it in terms of, pretend a hertz is a millimeter. Okay, use a ruler to figure it out. And you can scale it like that. So what's going to happen is in that first one, you're going to get a nice wide trans coupling like this. Then that allylic coupling is going to give you a small quartet. And so ultimately your peak are going to look like 2 small quartets like this. And if you look at that sample, it's going to look something like that. Okay. So notice in this spectrum how you can kind of see 2 quartets. Imagine that this is a little peak here, 2 peaks up at the top, and then 1 peak over here. Right? Same over here. It's like 2 little quartets. The reason they don't look really nice is this is at the limit of the spectrometer resolution. So this spectrometer that this was taken on, I'm not quite sure what that resolution is. I would guess that it's about 2 hertz coupling, so it's pretty small. Our spectrometers that we use here are better than this for the most part, so if your sample is nicely prepared and things, you should be able to see this a little bit more clearly. It would look more like 2 little quartets rather than like lumpy blobs. Okay? But that's the general idea here is you have 1 big coupling and then 2 smaller quartets because of the difference in the splitting in these quartets. How is this now going to differ from the second one? Okay, the second one has a big coupling, so it's going to be same to start. But now this quartet is going to be broader. It's going to be wider than it was in the first example here. Okay, because that second set, each of those splittings are now going to be 7 hertz instead. Okay, so if we draw that out, it's going to look like this. Note how they start to overlap in the middle. Okay, so you will see this when we start looking at experiment 17. Those things overlap. And ultimately, when you look at it, it's going to be two quartets. Now you see that they're much wider quartets and they actually overlap. So this quartet on the left is this peak, these two big ones, and that small one. And then the second quartet is these three peaks here and this peak there. So they overlap one another. Okay? And so you can imagine you can get some really funky looking peaks based on this sort of kind of overlapping couple. Okay? When you're predicting them and drawing them for experiment 16 there in your worksheets, again, like I said, I would suggest just go ahead and drawing whatever scale you'd like, make it in millimeters or maybe 2 millimeters per hertz or whatever else. And if you actually go ahead and measure the distances as you draw your little coupling trees like this, that will help you draw these and predict what these signals are supposed to look like. All right, any questions on that? Okay, so keep in mind